Our newest tool is the change of variables formula. Pass a continuous random variable through a smooth monotone function, and the density transforms by the slope. This video points that formula at one special function, the CDF itself, and theory becomes an algorithm. First, feeding any continuous random variable through its own CDF flattens it to a uniform. Then we run the map backwards. The inverse CDF turns uniform draws into any distribution we want. We work the recipe end-to-end for the exponential, and a binning trick handles discrete targets too. That closes Chapter 9. Derive forward, generate backward. Start with the engineering problem. Simulations need random variables of every shape, exponential arrival times, Gaussian noise, discrete packet counts. But the computer offers exactly one primitive, a routine that returns a value uniformly distributed between 0 and 1. The goal of this video is to manufacture everything else from that single routine. Here is the observation that unlocks it. Take any continuous random variable x with an invertible CDF and feed x into its own CDF. Define y equals f of x. On the support of x, the CDF is differentiable and strictly increasing, and its derivative is the density itself. So last video's formula applies. The density of y is the density of x divided by the absolute derivative of the CDF, and that is f of x over f of x, which is 1. 1 for every y between 0 and 0 outside, because a CDF never leaves the unit interval. The bumps cancel perfectly. Wherever x is likely, the CDF climbs fast and spreads those values out. Wherever x is rare, the CDF barely moves and packs them together. Every continuous random variable passed through its own CDF becomes uniform on the unit interval. If the CDF is a bridge from any distribution to the uniform, cross it in the other direction. When f is invertible, applying the inverse CDF to f of x returns x itself. So take y uniform on the unit interval and define v equals f inverse of y. Derive distributions once more. The density of v is the density of y divided by the derivative of the inverse map, which is the density of y times the derivative of f at v. The uniform density is 1, so what remains is exactly the density of x at v. The variable v has precisely the distribution we wanted. Watch it work. Uniform draws rain down the vertical axis. Each one slides across to the CDF curve and drops to the horizontal axis. As draws accumulate, their histogram grows into the density of x. Where the curve is steep, a wide band of uniform values funnels into a narrow interval, so the samples land densely, exactly where the density is high. Where the curve is shallow, the samples spread thin. This is the inverse CDF method. To generate a random variable with CDF f, apply f inverse to a uniform draw. One uniform routine generates any continuous distribution. The recipe deserves one full workout. Target an exponential random variable with parameter lambda. Its CDF is 1 minus e to the minus lambda x for x at least 0. Inverting is algebra. Set y equal to the CDF, solve for x, and out comes f inverse of y equals minus 1 over lambda times the log of 1 minus y. So the generator is one line x equals minus 1 over lambda times the log of 1 minus y. Take lambda equal to 1 to keep the numbers visible. Feed it actual uniform draws. 0.13 becomes a short weight, 0.42 a moderate one, 0.91 where the logarithm climbs steeply becomes a long one. Small uniforms map to short weights and draws near one stretch deep into the tail. The change of variables formula confirms it. Differentiating pushes the uniform density to lambda times e to the minus lambda x, exactly the exponential density. This is how a simulator makes arrivals. Draw a uniform, take a logarithm, done. Discrete targets need one twist because a staircase CDF has no inverse. Bins do the job instead. Take a PMF on values x1, x2, x3 with masses 0.2, 0.5, and 0.3. Its CDF climbs in jumps, 0.2, then 0.7, then 1. Now slice the unit interval at exactly those heights. The first bin runs from 0 to 0.2, the second from 0.2 to 0.7, the third from 0.7 to 1. Each bin's length is exactly the mass of its value. The generator is a case statement. Draw y uniform and output xi when y lands in bin I. Watch the draws fall. 0.13 lands in the first bin, output x1. 0.42 second bin x2. 0.77 third bin x3. The probability of outputting xi is the probability that a uniform draw lands in its bin, and that is the bin's length, f at xi minus f at xi minus 1, which is exactly the PMF at xi. The video that introduced CDFs proved that a discrete CDF's jump heights are the probabilities. Here, the risers become sampling bins. One caveat, a naive case statement can be slow, and many discrete distributions have far more efficient generators. That closes Chapter 9. The key idea, the CDF is a two-way bridge. Run it forward to derive distributions, run it backward to generate them from a single uniform routine. Coming up, moment-generating functions.